Video, we're going to be talking about nomenclature, or how we name different molecules. So the first thing that we need to know is that the naming that we're going to be using is going to be known as IUPAC. And this is going to be a universal naming system developed by the International Union of Pure and Applied Chemistry. So everybody in the world looking at these different molecules is going to be using the IUPAC system, especially for the basic chemistry that we are going to be doing. Now, compounds use their naming system to ensure that everybody is able to know what the compound is. And so, no matter what language it is, the IUPAC system is going to be the same. And that is going to be how we are able to collaborate with other people who may not be able to speak English, or, for example, those in like Germany are able to know and everything what the compounds are that other people create. So, kind of understanding why chemical bonds form in the first place. So, atoms will form chemical bonds in order to become more stable. And they are going to achieve this stability by achieving an octet. And so, that and everything is just looking at the 8 valence electrons that all atoms want to have. And so, kind of remember how we determine reactivity from element or from unit 3. Okay, they are going to want to get to 8. The closer they are to 8 valence electrons, the more reactive they are going to be. And so, just really hitting home and everything, this idea that the atoms want to achieve an octet, those 8 valence electrons. Now, before getting into the actual naming system itself, we do need to talk about the types of bonds that we are able to look at. So, the first is going to be our ionic bond. These form between metals and nonmetals. And how these bonds form are going to be when the electrons are transferred from one element to another element. And that is going to be what creates an ionic bond. Next is going to be a covalent bond, which are only formed between non-metals. Now, our covalent bonds, the electrons are going to be shared between the different nonmetals. And so the sharing electrons is what creates a covalent bond. And then the last one is going to be a metallic bond, which is going to be formed between metals, in which case the electrons are kind of pooled. So all of the electrons inside of a metal are kind of just free floating, and this is going to be known as the sea of electrons. And this is really coming up with the idea of why our metals are going to be really conductive. So electricity is going to be a movement of electrons, and so with this sea of electrons, those electrons are going to be able to easily move, which is going to be what electricity is. And so they are going to really love to use this phrase of sea of electrons when talking about metallic bonds. Now, talking about bonding and electronegativity. All right, our electronegativity is an atom's ability to attract electrons. It is going to be really what determines the type of bond that forms. So, our ionic bonds have a really large difference in electronegativity. So, if we remember back to our unit 3, fluorine had the highest electronegativity, while francium had the lowest. So, francium being a metal, having our lowest electronegativity, our fluorine being a nonmetal, having the highest, that is going to cause a really large difference in electronegativity. The larger the difference is, those electrons are essentially going to be stolen, and we are going to create an ionic bond. Now, our covalent bonds are a little bit more complicated. So, a small difference in electronegativity will make it polar. So, whenever we have nonmetals, they have very closer electronegativities to them. And so, if they have a small difference in electronegativity, it will make it polar. But if we do not have a difference in electronegativity, it will make it nonpolar. And so, a really good example of polar would be water. So, H2O. H2O is considered to be a polar molecule because the oxygen is electronegative, and it is going to pull those electrons a little bit closer to the oxygen. Now, a nonpolar would be O2. So an oxygen molecule would be considered to be nonpolar because it is two of the exact same atoms and they're going to share those electrons equally. Let's go ahead and take a look at a few questions. So, question number one: what organization developed the universal system for naming chemical compounds? And so, this is just taking a look at the organization that really came up with these rules that we are going to follow. And we should get B, the International Union of Pure and Applied Chemistry. Number two: why do atoms form chemical bonds? So, kind of remembering from Unit 3 and what we just talked about, these chemical bonds are really going to be forming in order to make sure that the atoms become more stable. So, that is the entire reason why things react. They want to get to our 8 valence electrons, and that is the most stable form. Question number 3: what type of bond is formed when electrons are transferred? And so the really big word that we need to pay attention here is going to be transferred. Okay, so if these are transferred, that means and everything that this is going to be an ionic bond. Okay, so transferred is going to mean ionic. Question number 4: which statement correctly matches bond type with electronegativity difference? So remember that if we had a really large difference in electronegativity, this would be an ionic bond. So our large difference, this is going to be ionic. Now, if we have a small difference, this is going to be a polar covalent bond. Now, if we have no difference in this, this is going to be called a non-polar covalent bond. And so by taking a look at that, this is going to lead us to answer C. So no difference would be a non-polar covalent bond. Let's take a look at question number 5. Which element is the most electronegative? So this was not specifically written down, but I did say it. So the element that is the most electronegative on the periodic table is going to be fluorine. So remembering that we're going to follow our trend for electronegativity, which is up and to the right, but we exclude those noble gases over here. So the noble gases do not have electronegativity, and our fluorine is going to be in that top right corner. So fluorine will be our most electronegative element. Taking a look at question number 6. In metallic bonding, electrons are best described as. So we kind of talked about this a little bit, looking at our metallic bonding. And so the big thing to remember with the metallic bonding or our metals is this idea of the sea of electrons. And if we think of a sea, that the water is just kind of mixing, it's kind of not all in one place, it's able to move around. And what we're going to end up with is that these electrons are going to be pooled and delocalized, meaning that they're not just in one space, they're able to move around. And they're going to move around through a lot of different atoms. And this is what causes our metallics to be conductive. Number 7, explain why the IUPAC naming system is important for scientists all over the world. Give an example of how it prevents confusion. So, the real idea for this is that the IUPAC naming system will provide specific ways to name compounds, and this allows it to be used essentially worldwide. And this really will help prevent confusion because if we have, let's say, scientists in the United States and then scientists in Italy, let's say they come up with a compound together, they may want to name it slightly differently based on their language. But according to the IEPAC naming system, their name would have to be the same. And so that compound that they created would be able to be used by anyone in any language. Question number 8. How does electronegativity determine whether a bond is ionic, polar covalent, or nonpolar covalent? Provide one example for each type of bond. Well, if the electronegative difference is high, then the compound will be ionic. Now, a really good ionic compound, as an example, would be our NaCl. So salt would be a ionic compound. If the electronegative difference is small, the compound will be polar covalent. The most common example that we are going to run into is going to be H2O or water. And then if there is no electronegative difference, then the compound will be nonpolar covalent. And the example that I used when talking about in the notes was oxygen, which is going to be O2. So these are going to be what determines whether or not something is ionic, polar covalent, or nonpolar covalent.